Hello and welcome to Unit 8, Kinetics and Equilibrium, Lecture C. Today we're going to talk about what equilibrium is. So equilibrium, the fancy way of saying it, is a state of balance between two opposing reactions. I like to say it as the rate of the forward reaction is equal to the rate of the reverse reaction. Rate of the forward equals the rate of the reverse. And it's very important that you think of it as the rate and not the amount. The reactions haven't stopped. That's our first step. In order to have an equilibrium reaction, you have to have a closed system where all of your reactants and products stay in the system. If something is producing a gas, it's going to have to be in a sealed container, because if the gas can escape, then you've lost part of your reaction. It will do what we call going to completion. So let's talk about what types of reactions can reach equilibrium. The first step is they have to be reversible. So a reversible reaction means that both the forward and reverse reactions can happen. Forward and reverse are just what they sound like. We read from left to right. So when you read a reaction, as you go from left to right, that's called the forward reaction. And then right to left would be opposite of the way we read, so that's the reverse reaction. So they'll show this with double-sided arrows. If they draw you double-sided arrows in between, so notice that arrow is different than what you normally see, that means this reaction is reversible. The hydrogen and chlorine makes hydrogen chloride, and the hydrogen chloride can break back apart into the original hydrogen and chlorine. Okay, so forward reaction left to right, reverse reaction right to left. If you see just a one-way arrow, then they are assuming that that is not an equilibrium reaction. So double arrow, it's reversible. We can do both directions. When we start an equilibrium reaction, the forward reaction is going to have all kinds of reactants. And that reaction is going to go really, really fast, because there just aren't any of the products there yet to do the reverse reaction. As we make more of the products on the right side, then that reverse reaction picks up speed and starts to go faster and faster. Eventually, you hit a point where the forward reaction is going at the same rate as the reverse reaction. So the left to right reaction goes just as fast as the right to left reaction. The forward reaction and the reverse reaction are at the same rate. Notice it's not amounts. Both reactions continue to happen. So we say that this type of reaction is dynamic because the reaction is still going. When you look at it, it will look like it stopped. So for example, when we dissolve ionic compounds in water, we typically don't think of it as being a reversible reaction, but we end up with our positive ions and our negative ions in our aqueous solution. That's where the water went, so there's still water here. When we reach a saturated solution, we said before that a saturated solution was at solution equilibrium, because the rate that the sodium chloride is breaking into sodium and chlorine ions is equal to the rate that the sodium ions and the chlorine ions bump into each other and turn back into a sodium chloride particle. So the rate of the forward is equal to the rate of the reverse. It doesn't mean that the amounts of solid sodium chloride and the amount of sodium and chlorine ions are equal. The amounts have nothing to do with it. It is the rate that the forward reaction and the reverse reaction are happening. When the rates are the same, we are at equilibrium. When the rates are the same, we are at equilibrium. If we look at some graphs to try to explain what equilibrium means as far as the rates being the same, if we graph with the rate as our y-axis, and this line, I'm going to make orange as your forward reaction, it starts off really, really fast, which is what I was explaining before, because you have a lot of reactants and you have absolutely no products yet. So your reverse reaction has to start at 0 because there are no products. As we make more products, the reverse reaction starts to speed up and it goes faster and faster until they reach a point where the rates of the two reactions are the same. So notice that the line meets if we're graphing rates, and the rates are the same. This section right here, where they're the same, is equilibrium. But look at what happens if instead of graphing the rate, we graph the concentrations. If we have an equilibrium reaction where we're graphing the concentrations, again, our reactant is going to start off really high up here, and here they've already used two different colors, so it's easy to see. Here's our forward reaction. Our forward reaction starts off with a high concentration, and our reverse reaction starts off with a 0 concentration because there are no products yet. As the reaction proceeds, the concentration of the forward reaction decreases, and the concentration of the reactant or the products increases, and eventually the concentrations stay the same. So concentration stays the same, stays stable. I guess stable would be the best word that I want to use. They're not equal to each other. Notice that the concentration of A and the concentration of B are not the same. They are just unchanging. Same thing happens over here with reaction 2. These are different reactants. Again, we have, they're looking at the reverse here, a lot, and it steadies out right here where they both flatline out and the concentration is staying the same, staying stable or unchanging. This is where we are at equilibrium. So at equilibrium, the rates are the same and the concentrations don't change. The rates are the same, the concentrations don't change anymore, but the concentrations do not have to be equal. Okay, we can change that equilibrium point once they reach equilibrium by changing the conditions that our reaction is at. So once we reach an equilibrium where their concentrations are staying the same, they're unchanging, I can change those concentrations and push one reaction faster than the other. So we can push the forward reaction or we can push the reverse reaction and make one of them go faster. So we can shift it. If I make the forward reaction go faster, then I say I'm shifting it to the right. If I make the reverse reaction go faster, then I am shifting it to the left. So if the reverse reaction goes faster, it's shifted left. If the forward reaction goes faster, it's shifted right. And all I have to do is follow the arrows to see that. The forward reaction goes from left to right. So if that one goes faster, I'm shifting right. And the reverse reaction, the arrow goes from right to left. So if I make that one go faster, I am shifting it left. Changes in equilibrium is something called Le Chatelier's principle, and we will talk about that in Lecture D.